Hello everyone. I'd like to thank the organizers for the invitation. In this talk, I'll discuss the first experimental demonstration of a new approach to detecting ultralight dark matter using two optical cavities. According to the standard model of cosmology, known as lambda CDM, we know that 25% of the universe consists of dark matter. Evidence of dark matter ranges from galaxy rotation curves to the cosmic microwave background. Based on these observations, we infer that the range of possible dark matter masses spans almost 80 orders of magnitude. The focus of this talk is on the ultralight scalar, which acts as a classical field oscillating as a simple cosine, and couples to the electron mass and fine structure constant like this. This causes a change in the Bohr radius and hence an oscillation of macroscopic solid objects like an optical cavity at the frequency of this field, which we can detect using optical interferometry. Even in the absence of a discovery, we can set limits on these coupling constants dme and de. In this talk, I'll focus on dme, assuming de is 0. The resulting limits will apply to de as well. Now, as evident from this expression, the strength of the field depends on the local dark matter density. So let's look at its spatial distribution. As a reminder, the solar system moves through the galaxy as follows, and a spherical dark matter halo engulfs the galaxy like this, and our detector located on Earth sees a dark matter wind like this. From this plot, we can see that the dark matter density in our solar system is approximately 0.4 GeV per centimeter cubed. This is known as the standard halo model. In another model, we have a relaxion star bound to the Earth via gravity, in analogy to how the galactic halo is bound to the galaxy. This hypothesis is still consistent with observations as long as the density and radius of the relaxion star are given by these curves. The advantage of this new model is that it allows for terrestrial dark matter densities that are almost 12 orders of magnitude greater than the standard halo model. The corresponding rise in the field amplitude boosts our detector sensitivity by 6 orders of magnitude. Next, let's look at the velocity dispersion of dark matter. In the standard halo model, the dark matter velocity dispersion seen by a terrestrial detector is given by the Maxwell-Boltzmann distribution, centered close to the solar system's galactic orbit speed, and width given by the virial velocity. For the relaxion star bound to the Earth, the dispersion is almost 2 orders of magnitude narrower. These widths play an important role in the statistical properties of dark matter given in terms of the coherence time as follows. In other words, the dark matter field is stochastic, with the amplitude and phase being random variables drawn from these distributions. This simulation shows the behavior of such a stochastic field with the amplitude normalized by the average. It looks only like a cosine on timescales shorter than the coherence time. Note that the observed dark matter density of 0.4 GeV per centimeter cubed, say in the standard halo model, should only be used to compute the field amplitude when the detector performs sufficient averaging over the dark matter field. This property is an important consideration when discussing data analysis later. Having looked at some of the properties of dark matter, let's now take a look at how to probe it. Our dark matter detector is analogous to gravitational wave detectors, where oscillations in the length of one cavity are measured relative to the other. In both cases, we can define a strain associated with the fractional length change. The quadrupolar nature of gravitational waves causes the two arms to oscillate 180 degrees out of phase. However, for a scalar dark matter field, these cavities would oscillate in phase. So, to not get a cancellation from these two arms at the photodetector, we need to find a way to make these cavities oscillate out of phase. Recall that the dark matter field will drive oscillations in the cavity length like this. We can describe the dynamics of the process by a simple mass spring model. First, in the absence of dark matter, a cavity of length L0, mass m, and stiffness k is represented as such in the lab frame. Then, when you turn on dark matter, the system is now placed in an accelerated reference frame with a sinusoidal displacement like this. The dark matter drive appears as a fictitious force in this reference frame and causes this mass to oscillate with an amplitude a and phase offset theta relative to the drive. If you define the transfer function as the displacement of the mass in the lab frame relative to the drive amplitude, then a straightforward solution of the equations of motion gives this. We estimated the transfer function of our cavities by empirically measuring the resonance frequency and quality factor. Let's take a closer look at its behavior. For dark matter frequencies below the mechanical resonance, the mass follows the dark matter drive and the transfer function is 1. Above the resonance, the mass displacement almost completely opposes the displacement from dark matter, and the cavity length approximately goes back to its undriven value. In essence, the cavity is shielded from dark matter at higher frequencies, and we can now use this cavity as a reference to measure the length of another cavity. We measure the length of a cavity by measuring the optical frequency of the laser resonant with the cavity. As a reminder, in a Fabry-Perot cavity, multiple reflections between the mirrors results in optical standing waves, giving rise to a longitudinal mode spectrum like this, where the mode spacing depends on the cavity length. Then, length fluctuations in the spacer cause fluctuations in the frequency of the resonant mode with the following relationship. Now, our detector has two cavities, with the following longitudinal mode spectrum. On this photodetector, we monitor the difference frequency between these longitudinal modes. If we define an optical strain as this, then it's related to the dark matter strain through this detector response function A. Since we're measuring the difference frequency, A depends on the coherent difference mechanical transfer function, which can be visualized as follows. These red curves show the amplitude and phase of the long cavity, with the resonance frequency dependent on the length. Similarly, the blue curves are for the short cavity, and the dashed black curve is their coherent difference. If you park your dark matter frequency in the gray region, these cavities oscillate 180 degrees out of phase, similar to the gravitational wave detector's behavior we were aiming for. So, we call this our science band, which is also the region of highest sensitivity. Note the power of the differential measurement lies in the coherent subtraction, implying that dark matter-induced oscillation of these cavities maintain a fixed phase relationship with one another. That won't be the case for any incoherent noise sources. Here's an intuitive picture to understand the transfer function plotted here on a linear scale. Below the mechanical resonances of both cavities, the cavities follow the dark matter drive, so the difference strain measured at the photodetector vanishes. Above both mechanical resonances, since neither cavity responds to dark matter, their individual strain and hence their difference strain vanishes. Finally, in between the mechanical resonances, the short cavity follows the dark matter drive, but the long cavity becomes a length reference by effectively not oscillating in response to dark matter. So, the detector has the highest sensitivity in this frequency window, called our science band. Okay, so having understood the detection principle, let's look at the apparatus details. Here's a photo of the dark matter detection apparatus, where the breadboard is sending laser beams towards the cavities inside the cryostat. Here's a top view sketch of the apparatus. Moreover, here's a sketch of this section viewed from here. The design choices of this apparatus were driven by the target dark matter sensitivity. So, let's look at the contribution of every major component to dark matter sensitivity. Here's a simple optical layout and its section view. The thick black curve shows its dark matter sensitivity compared to other experiments. At lower frequencies, denoted by this colored region, we're limited by vibrations. On the right, we're limited by laser frequency noise. I'll show you a series of upgrades to this simple setup that can bring this curve considerably lower. Let's start with laser frequency noise mitigation. Adding a filter cavity here causes a reduction in the laser noise as shown in the transition from the thick black dashed to solid curves. Then, on the right, the bottleneck becomes room temperature thermal noise and photon shot noise. The vibration noise can be suppressed by hanging our two cavities from this multi-stage passive vibration isolation system. The thick black curve drops further, and now we're only limited by room temperature thermal noise and shot noise. The obvious next step is cooling down the apparatus. So, we put the vibration isolated setup in a 4 Kelvin closed cycle cryostat and get a significant boost in sensitivity as we're now limited by 4K thermal noise and shot noise. Next, let's take a closer look at the mechanisms through which these noise sources affect dark matter sensitivity. As a reminder, our apparatus is an optomechanical system where length oscillations from dark matter strain are read out optically. There are two types of noise sources, ones that cause length changes like vibrations and thermal noise, and those that cause optical frequency errors. Let's start with vibrations. Recall our simple mass spring model where our cavities were placed inside a reference frame accelerated by dark matter. Vibrations produce a similar effect. This can be partially mitigated by engineering the spacer such that the support points minimize the impact of vibrations. Furthermore, we can isolate the cavities with multi-stage pendulums. Let's see how they work. The payload is immune to vibrations through three types of pendulums. First is a geometric anti-spring filter made of 3 blade springs. This is supported by 3 inverted pendulum legs which can move at these flexures. And finally, there's a conventional single-wire pendulum. Here's a photo of this assembly, a zoom-in of the gas filter, and flexure. The inverted pendulum offers horizontal vibration isolation as quantified by this displacement transfer function. It's the same for the conventional pendulum. The anti-springs provide vertical isolation. The topmost anti-springs and the wire form the first stage. Here's a typical transfer function of the anti-springs, which saturate after 3 orders of magnitude improvement. A straightforward way to go past the saturation is adding more stages. Here's a photo of our 3 stages. Our final payload consists of these 2 cavities. Next on our list is thermal noise. In addition to vibrations, the random thermal motion of atoms inside our cavities also leads to noise in our measured strain. In our simple mass spring model, the drive comes from random kicks from these atoms. According to the fluctuation dissipation theorem, this effect is reduced at lower temperatures and using materials with a high quality factor, such as sapphire and crystalline reflective coatings. And we get to lower temperatures using cryogenics. So let's take a look at our cryostat. We can gain almost an order of magnitude reduction in thermal noise by going to 4 Kelvin inside this vibrationally isolated cryostat. Only the final stage of the vibration isolation shown here is at 4 Kelvin. The rest of the pendulums are at room temperature separated from the cryogenic components via thermal standoffs. One of the most important features of our system is achieving optimal trade-off between cooling power and vibration isolation using these soft thermal links. Finally, let's take a look at laser frequency noise. Laser frequency stabilization is a mature field with a variety of techniques at our disposal. In particular, the Pound-Reaver-Hall technique is used for locking a laser to an ultra-stable cavity. Laser noise in our science cavities can be reduced by pre-stabilization to a ULE cavity. Noise suppression using Pound-Reaver-Hall relies on the cavity storing the phase while averaging the laser noise over the photon storage time tau, and the servo making the laser follow this average. But our dark matter signal depends on frequency noise, which is a derivative of phase, and the frequency stability is only inherited from phase for timescales longer than tau, as illustrated by this curve. One way to overcome this noise increase in our science band is by looking at the ULE's transmission. That's because the cavity acts as a low-pass filter with this profile, so the transmitted light does not experience higher noise at higher frequencies. So, by switching the geometry like this, we reduced laser frequency noise by almost an order of magnitude. This filtering technique is critical in our setup because our science band, which is controlled by the cavity's mechanical resonance frequencies, lies almost 2 orders of magnitude above the low-pass filter's corner frequency. In summary, this is our detector overview incorporating the noise mitigation schemes we just saw. Next, I'll discuss the results of our first dark matter observing run. As a reminder, the RF signal monitored on this photodetector corresponds to the difference frequency between the light transmitted by the 2 cavities. Oscillations in these modes from dark matter would show up as sidebands on the RF carrier. In order to extract the sideband information, the photodetector output is sent through this delay line frequency discriminator, which removes the carrier, and the output is saved on a computer as a time series using a data acquisition card. This self-homodyne scheme eliminates slow drifts in the carrier. For an initial dark matter observing run, data was continuously collected for 4 days. After a fast Fourier transform, we get the following strain spectral density, where we look for narrow peaks corresponding to dark matter. For example, in the standard halo model, if we zoom into this region, we expect to see a feature with a profile like this, with a width which scales as the inverse of the coherence time. This profile is a manifestation of the Maxwell-Boltzmann distribution we saw earlier. Moreover, the narrowness of this profile allows us to rule out these peaks of technical origin, which are simply local elevations of the noise floor if you zoom in. The noise floor is described by white Gaussian noise in frequency windows on the order of the dark matter profile. Using variances extracted from such fits, we can define a 95% confidence detection threshold as follows. Since none of the points in the raw spectrum lie above this threshold, we do not find any evidence of dark matter on our first observing run. Nonetheless, we can use our noise level to set exclusion limits on dark matter. As a reminder, we want to set a limit on this parameter DME, which represents the strength of coupling between dark matter and ordinary matter like the electron. Our detector measures this strain, which is related to the dark matter strain as follows. As a reminder, A is the detector response function related to the mechanical transfer functions of the two cavities. Under the assumption that our detector noise is much greater than the dark matter term, since we don't see a feature like this in our spectrum, we can use Bayesian analysis to estimate DME. Assuming a dark matter Compton frequency of, say, 50 kHz, and using the noise data and this line shape function as inputs, we can compute the following probability distribution function of DME. By integrating this function to 95%, we can exclude values of DME above this line with 95% confidence. Then, by sweeping the center frequency of dark matter, we can compute DME as a function of Compton frequency as follows. Now, let's apply this technique to the two models we considered. In the standard halo model, the new DME versus Compton frequency parameter space we explored is shown by the gray regions. The new limit is improved by up to 2 orders of magnitude. Here's a zoom in of the region in the red dashed box. In the case of the relaxion star bound to Earth, recall that the dark matter density is 12 orders of magnitude greater than the galactic halo. This results in a boost in our detector sensitivity because the field amplitude grows with ρ, as evident from the limit on DME being almost 6 orders of magnitude lower. However, note that our detector sensitivity suffers at frequencies below 34 kHz, where the measurement time is shorter than the coherence time. For an intuitive understanding of this sensitivity hit, let's revisit the time domain simulation of the stochastic dark matter field. As I stated in the introduction, this simple relationship between the field amplitude and dark matter density is only valid when the detector has performed sufficient averaging. For timescales much shorter than the coherence time, if our detector happens to sample, say, this point with a small amplitude, then our sensitivity of dark matter would be reduced. Such a statistical sensitivity hit can be adequately modeled by the Bayesian inference method I discussed 2 slides ago. In summary, I have presented a new approach to detect dark matter using optical cavities. While we didn't find dark matter, we improved previous limits by up to 2 orders of magnitude for the standard halo model and the relaxion star bound to Earth. With the lessons learned from our first dark matter observing run, our detector is capable of almost 4 more orders of magnitude improvement in sensitivity with future upgrades. Finally, I'd like to thank the members of our team at Northwestern, our funding agency. I'd also like to thank these individuals for useful discussions. Thank you for your attention.